will stop. Did you see that? Yes. We can do it again. We can do it again. Now the interesting thing here is I know it stopped because it should stop. Why should it stop? Why should it stop? Come on, guys.
Black.
It's black. It's in the black state. It's not stopping because it's out of batteries. It's not stopping because there is a problem with the sensor. It's not stopping because there is a bug in my algorithm. It's stopping because it should stop. It's important. That's because there's not enough light. That's the problem with these sensors. They are of very, very low quality. So if there's not enough light, it's not going to work. So now what's happening is it's turning around in circles because it doesn't have enough time to really detect. Now it detects time. Stop. Okay, so now we have half of our behavior. Actually, what we want to do is we want to write the other half of the behavior, which makes it follow the line, which is what happens when it's in white. Sorry, what happens when it's in black? So I'll just paste it here with some black, so it will start moving. And there's the syntax error.
Johan, a question.
Yes?
How do you know it's stopped? Because it's in the black state, because you don't have a battery low state or something like that.
It would be a big coincidence. Because actually what would be happening is that the machine, okay, try with the flashlight. Let's see if that works. It's on. Right, it's on. Let's see what happens here. Let's try it here. So the reason yes, thank you. See it by the flashlight. So I'll answer your question a bit later when I stop playing here. So you can see that when it detects black, it goes one way. When it detects white, it goes the other way, except that it doesn't always work because there's not enough light. And this is why it's Lego and not a machine which costs the price of the Ferrari. Because with the Ferrari, yeah, it would detect it. Now it's totally going crazy, but that's basically okay. Let's leave it 30. Thank you. So it would be a very big coincidence that the battery would die and it would register black at the same time. Because if it's registering black, this is because this machine read this sensor said, yeah, it's black, and sent that back, and then before this machine could tell him that he should stop the motor, the battery died. It's technically possible, but the probabilities for that are extremely, extremely low. So my point is, you won't be able to rule out everything, of course. But in this case, what happens is, I can see the state, so I know what's happening, right? And now I can also play with the parameters. I can think, okay, yeah, this guy is actually going much too slow, so I can take the speed, which is now 9, and I can change it to 90. No, I want this one. So it stops when it's detecting black, because when it detects black, it goes on the state. And of course, you always have the big red button. With a robot, you should always have the big red button, which basically kills it. So, in this low light situation, it could be much nicer. You can't see it much. I hope this afternoon outside with the sunlight, it will work better. Please trust me, it can actually follow the line and go all the way around. We'll do it this afternoon. So the point here, the second thing is I can change my code, I can play with my parameters, my epsilon parameters, and I can fine-tune the speed at which it turns to the left, it turns to the right, to be able to ensure that it makes very difficult curves without any problem, because when it goes too fast, it's going to end up outside of the paper and all that kind of situation. And the point is, I can do it while the robot is here doing its thing. One key press makes it change its behavior immediately. So I have this immediate connection from the code to the state machine to the robot running. Immediate connection from the state machine back to the code. Yes?
Yeah, I have a question. So I have a question regarding your script. So your script, yeah, so your script like is very concise, very small, but it's written in a very optimistic way. So you're assuming that everything is going to work. But my question is like, why you're not dealing with errors? Because
it's a silly example.
Yeah, but I think it's a very central point, because you have to deal with error all the time.
Yes, robots. Yes, of course, you have to deal with errors all the
such as, for
time.
example, now black, right?
Yeah.
Case in your error.
What happens when you're programming robotics is you have errors all over the place all the time. And you need to deal with this. This is why you use hierarchical state machines. This would be a standard behavior, which is lower in the hierarchy of another kind of behavior. And the other kind of behavior, for example, would catch this kind of errors, which catch a low light condition. And if it's a low light condition, the state machine which is higher will go to a different state, which is the low light state, which means that this behavior disappears, and inside of the low light state it will do some other kind of stuff. That's the reason why state machines are used. They have been very successful in the Robocup competition, all that kind of stuff. It's not here because it's a silly example, but yes, you can do it. All right, that's the demo for now. Just go that over there. So remember, tonight, if you want to play with Lego, I'm here. So back to the presentation. There's a question. Oh, sorry, I didn't see.
How much does Nora cost?
For me, she was free. But this is the EV3 Education Edition together with the expansion pack. But you can get the version without the expansion pack, and I think it's 250 euros. I should check, because this one I got it in Chile. I didn't get it here in Europe, so I think it's about that amount. It's that amount of price. It's a toy. It's an expensive toy, but it's still a toy. Okay.
Approximately zero. Approximately zero.
So, immediate connection. Two kinds of immediate connection. I edit my source code, immediately something happened. Right? The machine, Dora was standing there, we didn't give it any behavior yet of what to do when it was in light. I copy, I paste, it does it immediately. Right? Didn't have any behavior what to do when it was in black. I copied, I pasted, did it immediately. Immediate connection. Immediate connection. The machine, state machine, is telling us that Dora is in the black state. So I know why she's doing that. She's doing that because the state machine visualization tells us she is in the black state. Immediate connection. From the code to the behavior, and from the behavior back to the code. So this is where I was going to do that one, but I already did it. So usually I say more about language in the paper, but it's not this kind of conference. So on the website you will have much more information. I am going to show you one more video since we have the time apparently. So this is work that Pablo did when he was doing the internship at École de Miguel, where you can see that it actually runs on robots which are not toys. So here again you saw the robot was going forward because it was in the forward state. It stopped now because it's in the stop state. Let's do a little fast forward. We have a bit of a more complicated state machine where depending on where the robot sees the obstacle, if the obstacle is to the right, it's going to turn to the left. If the obstacle is to the left, the robot is going to turn to the right. And Great. So you see now it's turning to the left. It stops for a moment, goes forward, it goes to the left, stops, it goes forward. So you see that the reason why it's doing that, because it needed to turn left, because it needed to turn right, etc. etc. I can't see much of the robot will come back. There's the robot. This is Pharo. So this is part of Pharo. And the point is, writing this kind of behavior, where usually you will take hours, you can do it in 15 minutes. This bouncing off of the line behavior, I did it in 10 minutes. If I would do it in the way that my students were doing it with Java on the other machine, it would take me a couple of hours. Because you need to fine-tune everything. And it takes you a whole lot of time. So yeah, this was work together at Code in the Duet. Alright, conclusions, almost there. So this is an experiment. This is an experiment in how far can we push dynamic programming in a robotics context. If you think about people writing robot software, they're doing this in C, they're doing this in C++. If they're lucky, they're doing it in Python. Right? So what I'm doing here is I'm going to the totally the other extreme. And I want to see, can I write code where it's live? So yes, you can. It's possible. I have a couple of experiments that show you that you can do it. It works. State machines are actually a very robust paradigm to write live programming code. While I won't expect you right now, but you can do a lot of changes before you need to program to restart. Concrete experiments, concrete experience that we did. Using live robot programming, you can program your robot incredibly fast. It's really a radical speed up. And why do we have this radical speed up? Because you have an immediate connection. Somebody was listening, thank you. This is the point. The immediate connection. There is no disconnection between the idea in my brain and the thing which is actually happening, because I can edit it on the fly and I see things to happen on the fly. So we still need to do some stuff. We could write code in a better way, so we don't need to restart the program that many times. We are testing with smaller examples. We want to scale up to bigger examples to see if we can really express everything that we want to express. Right now, we don't have any module system. Once that the program starts to become bigger, we will need a module system we need to be able to use. And you can try it out. You can try it out on this machine. You can try it out on a big robot if you happen to have one somewhere. Also, you can try it out, just play with state machines if you want. Yeah, that's it. Questions? Yes, Steph was first. It was already.
Yeah. So I have 3 questions. Can you add a state dynamically?
Yes.
Okay.
Yes, that was what I was doing all the time. I started with the machine, added the state, added the machine, added the state. While the state machine is running, you can add state, you can remove a state, you can add transitions, remove transitions, you can change everything.
So I have a question. This is about debugging.
Good question.
Because what you use is that you see the state. Like,
yes.
Okay, I am in this state. But what would be, how do people debug Petri nets or this kind of diagrams or programs?
Yeah. Right now, what you see in the robotics community is they don't talk about debugging.
Yeah, but they don't care of them.
Yeah, but no, those are the guys who are using
The
this.
state machine, how people debug state machine? Do they just have a sequence of action and try to see if they have a reachability, if they reach the state, or?
Talking to people doing this, usually the question is, okay, I ended up in this state, but I don't know why I ended up in this state. I started there and I took a bunch of transitions and I reached there, and I don't know why. I don't know what's the path that I took. I don't know which transitions that I took, and I don't know why this transition triggered.
Okay, because what I was thinking, and this is my last question, this is, do you plan to have a kind of, you could have a trace of the execution, and it's more like post-mortem analysis?
Yes. Yeah. I've been thinking about this for a long time. I'm just missing a couple of students. Any more questions?
So, are you familiar with Seymour Papert Mindstorms, I guess?
So, yeah, so Mindstorms, actually this is called the Lego Mindstorms because this
Okay.
is based on
So-
evolutions of Seymour's work, yeah.
Okay, great. So, in that context, I'm curious to what extent the robotics, the focus on robotics is on the robotics per se, or robotics as a transitional device?
What I want to do in my research is I want to improve all of the software engineering aspects of robotics. Because what I see in practice is that almost everybody who's doing robotics, they don't know how to write software. They write stuff in C, and it takes them a long time to do very simple things because they need to start, recompile, etc. So this is an enabler for ideally everything that has to do with robotics. Ideally, I would love to use this thing also to teach to my students instead of having them need to write Java, for example. Does that answer your question?
So what I heard was that your focus is mostly on robotics per se.
Yes, software engineering for robotics.
Okay.
I can speak loud, so I don't need the mic, I'm pretty sure. The context that it was kind of part of my question, when you take it to other contexts and think about predictability of the system, of the software, it's kind of, it becomes a chaotic system, right? Very sensitive to initial conditions, very sensitive to environmental conditions and so on. So how do you see the applications of the software technique as life programming transfers to, say, finance or, I don't know, anything really?
Okay. So you want to talk just about the live programming paradigm,
Yeah.
not about robotics? I don't know. It's a very good question. So, as I said before, what I'm trying to do here is I'm trying to push towards an extreme. I'm trying to push to extreme liveness, extreme everything. This is obviously not viable in every context, in every kind of situation, etc., etc. What you could do, for example, to think about this language, is you could do a lot of fast prototyping until you get a state machine which is the behavior that you think which is right. And then if you don't like liveness, you take this, you write it in whatever you want to have the same behavior, and you use that, for example. But, yeah, at least it should be able to do fast prototyping kind of stuff, because the point of live programming is really this kind of direct connection where you have really, really fast development cycles. Okay? Saw some fingers before.
Same question, effectively. Is it really practical to have every keystroke transfer to the robot? I'm a very careful guy due to bad experiences during development. And so having a state where the code is acceptable, that means syntactically correct, happens very often. But the robot seeing the correct program and really starting off maybe something that I did not expect and do not want.
Okay.
So I would have the ultimate kill switch all the time enabled.
Let me show you.
But I see the point. So
Yeah, let me show you something since we're still okay with the time. Right, Steph?
Yes.
See? I can stop my interpreter at any time, for example.
Yeah.
So what I can do is I pause the interpreter, I edit my code until I'm really, really 100% and it's okay. I hit pause, it continues. That's one point. Like, just be very, very careful on what's happening. The other thing is, what I can do, let's pause it first.
we don't see the field strategy.
And effectively, we believe you if you
Ah.
tell it.
Then that way you don't see what I'm seeing. Okay, sorry. Silly mistake.
Yeah, okay.
I can pass the interpret, right? The other thing is, I can write code which syntactically is correct small talk, but cannot run. For example, so, for example, what I can do, for example, I can do something like, let's say I have a variable norm for normal, that I write nor it compiles to reference a variable that doesn't exist. When that block runs, it's going to throw an exception. Didn't run yet. When it runs, it throws an exception. The exception gets logged here. And actually what happens is this action, because this was an action where I said, okay, I need to do that with motors, simply gets skipped. Okay? So the entire philosophy behind this and error handling, if there is a problem, I'm not doing it. So if there is an action, small talk block that I can't compile or it throws an exception while it runs, I'm not doing anything. I just skip it. Which means that I either do not see an event which causes a transition to go, or I do not execute the motor action. So you editing the code will immediately see that something goes wrong, and you always have the big red switch.
Okay, skipping is good. Skipping is sort of a dangerous idea because just some action not being done does not mean that the robot doesn't fall off the desk.
Yes.
So
yes.
Skipping, I want something which says it's an exception to stop everything.
Yeah, you could do that.
Okay.
You could do that. You can, as I talked to Alex before, you can write your state machine in a way that it's hierarchical at a higher level. You detect an error, you go to a stop everything state. Okay, last question.
Last question. You said that smaller, but not pure small. It's your LPR.
Yeah, LRP is live robot programming. It's
and the blocks are small.
The blocks are smaller. So it's a DSL. It embeds Smalltalk inside of itself, and it's done in a really cool meta-level hacking way, which I can talk about for hours. It's really great, and it's fast. Huh? By the way, those blocks they execute bytecode. They're on bytecodes. Variables get looked up like normal variables, so there's no overhead, etc. It's a good trick. So, thank you for your attention, and I guess now it's time for lunch.